Indoor environmental quality credit 7 is thermal comfort. EA credit 7.1 is thermal comfort design. And 7.2 is thermal comfort verification. There's separate criteria for core and shell. Indoor environmental quality credit 7.1, thermal comfort design. For new construction in schools, they can both earn 1 point. The requirement is to design HVAC systems in the building envelope to meet the requirements of ASHRAE standard 55. Once again, memorize the different ASHRAE standards in this lead category. ASHRAE standard 55 refers to thermal comfort conditions for human occupancy. You need to demonstrate design compliance in accordance with the section 6.11 of this standard. You need to evaluate air temperature, radiant temperature, airspeed, and humidity. Additional requirements for schools are included for natatoriums. They must demonstrate compliance with the typical natatorium design conditions in Chapter 4 found in the ASHRAE Handbook. And additional requirements for core and shell include that the mechanical system must allow for tenant build-out to meet the requirement of the credit. This is taking into consideration that the developer does not necessarily have control of the tenant build-outs, but LEED does encourage that in the leasing agreements the tenants have criteria to meet the LEED standards. For projects that do not purchase or install mechanical systems, you cannot achieve this credit for core and shell projects. Indoor environmental quality credit 7.2, thermal comfort verification, is contingent on achieving indoor environmental quality credit 7.1, thermal comfort design. You need to implement a thermal comfort survey of building occupants within a period of 6 to 18 months after occupancy, one of the few credits that does have requirements after occupancy. For schools, you need to survey students grades 6 and above. And the survey should include assessment of overall dissatisfaction with thermal performance and comfort. And if the survey results indicate more than 20% of occupants are dissatisfied, a plan of action must be in place. So be prepared to hear something other than you want to. And many developers and owners want to avoid this, but overall, you want tenants to be happy, and this is a great way to get those results. There's an additional requirement for new construction to provide a permanent monitoring system. Indoor environmental quality credit 8 pertains to daylight and views. This is more heavily weighted for schools. As with many sustainable design and construction strategies, there's always a cost-benefit analysis. For these credits, it could be daylighting versus glare and heat, because proper lighting improves productivity, but bad daylighting design causes heat and glare can interfere with tasks and also with actually enjoying the views, because most tenants will actually close the blinds even if they had a fantastic view if glare is a problem. And excess heat from poor glazing design can alter HVAC needs as well. You could be exhausting your system with cooling needs. Potential solution is carefully modeling and designing the lighting. This has to do with holistic design of your HVAC, envelope, and overall lighting design. They are all interdependent on each other. Holistic design is important because you can solve glare and overheating problems by envelope overhangs, showing that how you design the envelope has to do with your daylighting and lighting control design as well. Indoor environmental quality credit 8.1, daylight and views, pertains to daylight. For new construction, 1 point is available. Schools, it's 1 to 3 points. Core and shell, it's 1 point. For schools, classroom spaces that meet the daylight criteria for 75% of spaces earn 1 point. 2 points if 90% of the classroom spaces meet the criteria. And in all regularly occupied spaces, 75% meeting the daylight requirements earn an additional point. And there is an innovation design point available for 95% of regularly occupied spaces, also meeting the daylight criteria. So 4 points total for schools possible. New construction in core and shell is similar for regularly occupied spaces. 75% of those mean daylight requirements, earn 1 point, and there's innovation design point available for meeting 95% of the regular occupied spaces. Option 1 to comply with this credit is a simulation. There are many great energy modeling softwares out there now for modeling how to optimize your daylighting controls. In the computer simulation, you need to show that a daylight level is between 25-foot candles and 500 have been achieved in at least 75% of all regularly occupied areas, or 90% for schools only to achieve that additional point. Modeling conditions should be taken on the equinox, which is September 21st or March 21st at 9 a.m. and 3 p.m. And projects that incorporate automated shades only need to demonstrate the minimum 25-foot candles have been achieved. So automatic shades can help with energy performance as well, having a synergy with energy and atmosphere optimizing energy performance. And theater space, there's a 10-foot candle minimum. You need to update the model as the design changes and develops, including changes to both the lighting design in the envelope and orientation of the building. This includes any overhangs, vertical fins, or shading controls. Option 2 is a prescriptive path for side lighting. Achieve a daylight zone value between 0.15 and 0.18. In order to calculate this, multiply the window to floor area ratio by the visible light transmittance. And windows must be at least 30 inches off the floor. Important to remember everything in orange highlighted here. Once again, a lot of memorization in this category. The ceiling must not obstruct a line in section that joins window head to a line on the floor parallel to the plane of the window. You need to include redirection or glare control devices to ensure effective daylighting. Here's a diagram showing that relationship taken from the LEED Green Building Design and Construction Reference Manual. So remember that window's 30 inches off the floor, and you're getting daylighting in 2 times the height of the window in the horizontal direction. A drop ceiling can obstruct this, although, so make sure that this is a clear line. For top lighting, the daylight zone under a skylight is the outline of the opening beneath the skylight plus, in each direction, the lesser of either 70% of the ceiling height, half the distance to the edge of the nearest skylight, or the distance to any permanently opaque partition that is more than 70% of the distance of the top of the partition to the ceiling. Skylights must cover 3 to 6% of the roof area and provide a minimum of 0.5 visible light transmittance. The gap between skylights cannot be more than 1.4 times the ceiling height. We'll see a diagram of a skylight in order to illustrate this criteria. For implementation, step 1 is to determine the window surface area that can count towards this calculation. Step 2 is to determine if you need to adjust the applicable window square footage. Draw a 63-degree angle from the top of the window to the floor. And if a drop ceiling blocks this line, draw a 63-degree angle from the vertical using the ceiling corner that obstructed the previous line as a starting point. The point where this line meets the window is a modified height. Here's an illustration of that. Typically, your daylight zone comes into the building a horizontal length 2 times the height of the window from the finished floor. But if there's a drop ceiling blocking, you take that 63-degree line from the window and drop it below the corner of that drop ceiling. And that's your modified height. The modified height then affects your modified daylight zone that results, and that's what counts towards this credit. Step 3 is divide the floor area into areas that will apply to each window bay and determine the floor areas. Then determine the window area that will pertain to each individual floor. Step 4, to determine the window to floor area ratio for each plan area and multiply it by the visual transmittance of the glazing. So we'll look at applying these equations. Step 5, if an area is not compliant, reduce the square feet of the floor area in the equation until the area is compliant. This will tell you how much floor area can be counted. Step 6 is to determine how far to extend the daylight zone around the skylights. It is the lesser of the following two: 70% of the ceiling height or half the distance to the edge of the nearest skylight. Here's a diagram of the skylight calculations. So you have the skylight in the peak. You have that 35% angle showing you how far that daylight area comes into the building. Permanent partitions can block that area, so it's important to take that into consideration in your daylight design. The third option for credit compliance is to demonstrate light measurements taken at a 10-foot grid. You need to measure foot candle levels at 30 inches above the floor. Only the square footage of the space that meets the 25-foot candle minimum, memorize that number, 25-foot candle minimum requirement, can count towards the calculations. Here's a diagram of what you would submit to show compliance with the measurement option 3. You would show the actual foot candle levels and highlight the non-compliant area. In this case, 77% of the space has over 25 foot candles daylighting. Therefore, it meets the credit criteria. Option 4 is doing a combination of the previous methods. So you can combine options 1, 2, or 3 to prove that 25 foot candles of daylight illumination is achieved in at least 75% of all regularly occupied areas. Schools have the option of achieving the additional point if 90% of regular occupied spaces meet this criteria. And projects using this option should supply daylight, redirection, or glare controls. For options 2, 3, and 4, exceptions will be considered when tasks will be negatively affected by daylighting. Always remember, when a credit criteria doesn't make sense for your building, but you think you're achieving the intent of the credit, you can apply a narrative to show why you meet that intent to potentially still earn the credit on a project. The LEED rating system definitely tries to work with practicality. It just tries to set a national standard for how to create high performance, sustainable buildings. Strategies to achieve this credit are building orientation, interior color schemes and lighting. So interior color schemes can include reflective material and light colors, and also photoresponsive controls for electric lighting. This could be integrated to an overall control system for your building. Shallow floor plates allow for more windows around the exterior. You need to make sure to control how much direct solar heat gain is happening with exterior overhangs or vertical fins, depending on which facade we're talking about, whether it's north, east, south, or west. We'll have different requirements for how you shade those effectively from the exterior. You also want to increase building perimeter. This allows for more people to have access for windows and views and daylight. The older buildings, if you look at an aerial, are often more like a key, where you have a lot of in and outs and courtyards. I used to work in the Dexter Horton building in Seattle, and even as a second-year intern, I had a window seat just because the building was shaped as an E, and most desks were along a window. Very enjoyable building to work in. Exterior and interior permanent shading devices. Light shelves on the interior can help light reflect further into a building, and then if you have a light colored ceiling, it can then bounce down further into the building. Louvers, blinds, fins, and shades all need to be integrated, and it helps to have a model to show how those interrelate, to have a comprehensive daylighting plan. with your electric lighting considered. High performance glazing can also help. If you have high performance glazing, you won't get as much solar heat gain, and you can actually have glazing that dims depending on how much daylight you want into the building in certain areas at certain times. This comes from automatic photocell based controls. This can also include blackout glazing. One example of automatic photocell based controls is at the University of Portland. Indoor environmental quality, credit 8.2, daylight on views, refers to views only. For new construction, you can earn 1 point. Schools, it's 1 to 3 points, and core and shell, 1 point is possible. The requirement is to achieve direct line of sight to the outdoor environment via vision glazing between 30 inches and 90 inches above finished floor for the occupants in 90% of all regular occupied areas. In plan view, the area is within sight lines drawn from perimeter vision glazing. This does take into account any high partitions, walls, or other vertical obstructions, like we saw with the skylight diagram before. In section view, a direct sight line can be drawn from the area to perimeter vision glazing. Keep in mind the line of sight can be drawn through interior glazing. So if you have conference rooms or offices within the interior of the building, consider interior glazing. For core and shell, you could provide a feasible tenant layout for the default occupant counts or known count if that is available. To get an exemplary performance point for this credit, you must meet 2 of the 4 following requirements. 1. Provide multiple lines of sight to the outdoors at least 90 degrees apart to at least 90% of occupied spaces. 2. Views must meet 2 of the 3 items. Plants and trees, other people, such as maybe plazas, or objects at least 70 feet beyond the edge of the window. So it can't just be looking into an alleyway with garbage cans, basically. 3. At least 90% of the regularly occupied spaces have unobstructed views within the distance of 3 times the head height of the vision glazing. 4th option, at least 90% of the regularly occupied spaces have access to views with a view factor of 3 or more. Remember, only 2 of these have to be met to get the exemplary performance point. And make sure to pay attention to the criteria in orange to memorize for the exam. For the calculations, to show the direct line of sight to perimeter glazing, you want to create a spreadsheet of all regularly occupied space square footages, and then using the floor plan, construct view lines at each window to determine the fraction of the space that has direct line of sight. For offices, the entire square footage of the office can be counted if 75% or more of the area has direct line of sight to perimeter vision glazing. If it's less than 75%, estimate compliant square footage. Classrooms and other multi-occupant spaces, only the actual square footage with direct line of sight to the perimeter vision glazing is counted. Here's a diagram showing the views on a floor plan, including interior glazing from the private offices on the interior. Also notice on this diagram that the circulation areas are counted as non-regularly occupied spaces in addition to the server room. Those do not have to meet the vision requirements. Daylighting benefits include estimated reduction in lighting energy use by 50 to 80%, which is decreasing your overall energy use. This has synergy with optimizing energy performance points. Daylighting can work in tandem with passive solar heat gain design. If you have a concrete floor or mass that can hold in that heat and release it into the evening, that's a good passive strategy to reduce your HVAC load. And also increase occupant productivity and comfort. Indoor Environmental Quality Credit 9, Enhanced Acoustical Performance, only pertains to schools. The requirement is that the building shell, classroom partitions, and other core learning space partitions must meet the Sound Transmission Class STC requirements of ANSI Standard S12.6 Acoustical Performance Criteria, Design Requirements and Guidelines for Schools. Most important to remember, Sound Transmission Class ANSI Standard S12.6. It's important to note that windows must have an STC rating of at least 35. That number is important to memorize. And that background noise from HVAC must be cut to 40 decibels or less in classrooms and other core learning spaces. To remember the STC rating of at least 35 for windows and the 40 decibel limit for HVAC noise in the background for classrooms and core learning spaces. Exemplary performance can be earned by achieving an outdoor background noise level at 55 decibels for playgrounds and 60 decibels for athletic fields and other school grounds, or an indoor noise level of 35 decibels. The last credit for the indoor environmental quality section is mold prevention, and it only pertains to schools. The requirement for schools is that the following credits must be achieved. Credit 3.1, Construction Indoor Air Quality Management Plan during construction. 7.1, Thermal Comfort. 7.2, Thermal Comfort Verification. And provide HVAC systems and controls designed to limit space relative humidity to 60% or less for all load conditions, occupied and unoccupied. This is really looking to prevent mold, another health concern for children. And implement an ongoing indoor air quality management program based on EPA's Building Air Quality, a guide for building owners and facility managers, a BOMA resource. To implement this, use an effective vapor barrier on the building envelope. Use extra ventilation in areas with high humidity, such as restrooms. Check air handling units regularly to make sure there is no standing water. This can attract bugs and other diseases that can come with that and health concerns. Prevent mold during unoccupied times, especially parts of HVAC systems that see extended breaks during the summer. Make sure sprinklers and stormwater runoff go away from the building. And also choose floor materials that do not trap water underneath carpets. So there's lots of ways for water to sneak around a building and cause mold. And these measures try to mitigate that as much as possible. You have made it through the most technical section of the LEED Building Design and Construction Rating System. Great job. Just looking at some case studies, which there'll be more exercises attached as well in your study material. But here are just some images of good daylighting and indoor environmental quality measures. This is the Yale Sculpture Gallery. The Yale Sculpture Gallery uses an innovative double skin envelope system for natural ventilation called CalWall. It's an active curtain wall system that incorporates separate sunshade layer that helps control heat gain. So when I was in architecture school at U of O, I did a lot of studies on double skin systems, and it really does depend on your region and concerns with humidity, heat gain, and other variations. In this case, sun shading to prevent solar heat gain was most important. You can see in the section how this goes all the way up the facade for multiple floors. So this helps with both daylighting and views, and natural ventilation, and even energy efficiency if operating correctly. Exemplary performance for the indoor environmental quality credits include Credit 3, Construction Indoor Air Quality Management Plan during construction. For core and shell only, you can enforce an indoor environmental quality plan through all tenant spaces. This could be part of your leasing agreements, called a green lease. For Credit 8.1, Daylight and Views. For new construction core and shell, provide daylighting for 95% of occupied spaces for schools, 90% daylighting in classrooms, and 95% daylighting for other occupied rooms. Credit 9, enhanced acoustical performance, outdoor background noise level of 55 decibels for playgrounds and 60 decibels for athletic fields, or indoor noise level of 35 decibels. And for mold prevention credit, it's on a case-by-case basis, but you can describe your innovative strategy to ensure you're meeting mold prevention provisions. As an exercise, look at this independent station case study and this bullet list, and I'll pause the webinar and write down for each bullet which credit you think correlates to these sustainable strategies. You can use your LEED AP Plus new construction checklist to help you along. After you've run through this exercise, restart the webinar and we'll discuss. Okay, are you back? The third largest solar PV installation in Oregon, 130 kilowatts, contributes towards EA Credit 2, on-site renewable energy. Extensive use of LEDs throughout the development applies to EA Credit 1, optimizing energy performance. Rainwater harvesting has multiple synergies. I hope you caught that. For the water efficiency section, rainwater harvesting, if it was used for toilet flushing, counts for innovative wastewater and also water use reduction. And rainwater harvesting also helps with stormwater management. And if it's reused for landscape irrigation during the summertime, that also helps with water efficiency credit. Green roof and landscape third floor courtyard. Remember, with going through these credits, you need to understand which credit it applies to, but the number isn't as important because the number will be of the credit will be included in the title of the credit in the multiple choice questions. Back to the list of synergies. Green roof and landscape third floor courtyard. Green roof can help with stormwater management, heat island reduction, restoring habitat, all in your sustainable sites credit area. Can also help with optimizing energy performance if it's insulating the roof. In this case, it was an integrated system where the green roof also acts as a ballast system for the PVs to prevent any uplift from wind. So it was actually a weight system on the back of the PVs. It also cooled the PVs by reducing heat island effect, which makes the PVs more efficient. So synergies with performance as well. For solar water heating, radiant floor heating and cooling. Now, if you saw the word solar and thought on-site renewable energy, credit 2, that is incorrect. Solar water heating doesn't produce electricity. It actually just helps with energy performance. So it pertains to EA Credit 1, optimizing energy performance. For water source, geothermal heating and cooling, this is another tricky one where it could seem like it's on-site renewable energy, EA Credit 2, but it's actually just helping with optimizing energy performance, EA Credit 1, because it's not actually producing energy, it's just helping making the HVAC system run more efficiently since it's water that is kept at a more constant temperature, preheated in the wintertime to the underground constant temperature, and pre-cooled in the summertime, reducing load. Daylight design, we just went over those indoor environmental quality daylight credits. This can also help with optimizing energy performance as well, synergy there. High efficiency displacement ventilation can help with optimizing energy performance. Recycled and reclaimed building materials, material and resource section 4 and 3. Low VOC paints and adhesives have to do with indoor environmental quality, low emitting materials section. Rapidly renewable resources have to do with MR credit 6. And remember to review the variations in rapidly renewable resources. It's not just bamboo. And in this case study, each resident is planned to get an electric car, which pertains to alternative transportation, low emitting vehicles, And also, there's a synergy with the opportunity in indoor environmental quality, increased ventilation, credit 2, because the more fresh air you have outside, the more natural ventilation you can bring in. And that concludes this series.